Okay, so as explained before we started the recording is that these are the first 4 topics in our course outline, and in today's session I would like us to discuss on chapter 2, that is linear programming, and chapter 3, transportation problem, and assignment problem, those 3. And I was saying that since the notes that we have here are quite long, I may not want to take you through a lecture. So I may want to go through the notes very quickly. Then we can identify any points that need clarification. So starting with the second topic there, which is linear programming. These are the notes that I've shared with you. Of course, there is the introduction. Then we have the essentials of an LP model. Of course, these are things you've seen if you have gone through the notes. Then we have the properties of linear programming model. Then the formulation of an LP. And this is important because an LP, being a model, has several components. And one of the components of an LP is an objective function. So the model will not be complete if there's no objective function. And the other component that must be there is what we call the set of constraints. Set of constraints. Usually these are resource constraints. Resource constraints. And what are some of the resources that we'll be dealing with? We have men, we have materials, we have the other one is what? We have men, materials, and machines, correct? I think you have been reading machines. There's another M which is missing. What is that?
And time.
The other M is money. For those 4 M's: men, machines, materials, and money. Okay, time is also there. Time is there because when you spend time, men spend time to get paid. Okay, so those are some of the materials that will be allocating, or that will be constrained to work within. If resources were not were abundant, then there will be no problem because we just get the resources as we want them. But because resources are limited, then we have to come up with a model so that we work within some constraints. Then apart from that, the other component of the model is that the non-negativity constraint, meaning that what you're calling the decision variables are either greater or equal to 0. So decision variables are like maybe the number of units that you're going to produce, and so on and so forth. Those are the x's, either x1, x2, they are all non-negative. Okay, so in an LP model, those 3 parts have to be there. We have to see the objective function, we have to see the resource constraints, we have to see the non-negativity constraint, those 3 parts. Then here is a general illustration of how an LP model looks like. Of course, there are so many unknowns, so maybe some of you will be uncomfortable with that. But mainly, this is the first component. This is the first component of the LP model. The objective can either be a maximization or minimization type of problem. Okay, so some of the things that you can maximize are things like profit, production levels, and so on and so forth. And there are various other things that you need to minimize, things like losses, wastage, and so on and so forth. Then here is a list of a set of resource constraints. So you are working within that set of resources. So that's the second part. This was the objective set of constraints, then the non-negativity constraint, the last part. So as you come up with a model, you need to always confirm that those 3 parts are there. And of course, before you do that, you need to define your decision variables in every case. So let's see if we have an example like this one. So you're told a biscuit manufacturing company plans to produce two types of biscuits, one with the round shape, another one with a square shape. The following resources are used in the manufacture of the biscuits. We have raw material, of which daily availability is 150 kgs. So you see, this is the daily availability. That means you can't have more than 150 kgs in a given day of raw material. So that is calling for, you must work within less or equal to some 150 something. So here now there's an equation. Then machines, daily availability is 25 machine hours. That means you can't have more than that. So you'll be working within 25 machine working hours. Then labor, of which availability is 40 man hours, like that. So again, you need to work within those constraints. Then you are told the resources used are shown in table 1. And then you are told if the unit profit of round and square biscuit is 3 shillings and 2 shillings respectively, how many round and square biscuits should be produced in order to maximize profit? So this is your objective. Your objective is to maximize profit. Your objective is to maximize profit. So then we have this additional information. For now, we are not concerned with this answer. We are only focused on formulating the LP at this stage. So the starting point is to define your decision variables. What is unknown, or what do we need to know here? What we don't know here is the number of each type of biscuits to produce. We need to know how many of each type of biscuit do we need to produce so as to maximize profit. And that's how you define your decision variables. So you let X1, or you can just call it X, be the number of round biscuits to be produced. That is unknown. These are unknowns. And they are the values that we are looking for. At the end of the day, we need to find their values. This is another unknown. You're calling X2 the number of square biscuits to be produced. So if you know the number of round and square biscuits to be produced, then you can define an objective function here. So your objective is to maximize a function which looks like this: 3 of X1, because 3 is the price of is the profit per unit of a round biscuit, plus 2, which is the profit per unit of the square biscuit, times X2. We need to get maximum value for this. We need to get maximum value for that. So that is our objective function. Then what constraints are we working within? Okay. So from this table now, these are the 4 M's. The 4 M's are here: the machine, men, etc. So the first constraint is raw material. And you are told that a round biscuit requires 100 units of raw material, and a square one requires 115 units of raw material. And the daily availability of raw material is 1,500 units. So we need an equation that will help us to capture that. And that is what we have here. So we need 100 units of X1 plus 115 of X2. But when you add that, you cannot go beyond 1,500. You cannot go beyond 1,500. Okay, and you do the same for the other set of resources. So we have 10x, 10x1 plus 12x2 less or equal to 720, and so on and so forth. So the same story. So those are the set of constraints. Then once you are done with that, you need to write this. By default, you write all the decision variables must be greater or equal to 0. In other words, you cannot produce negative units. X1 cannot be a negative value. That's what it means. Huh? So X1 and X2 are non-negative, can never be negative. Because it doesn't make sense for you to say that X1 is, let's say, minus 10. Because what do you mean that you are producing minus 10 units of round biscuits? Doesn't make sense. So once you have all that, this is now how you report your model. So this is how your model will look like. So what was happening up there was the working. It's like you are the steps, but this is now the required answer. This is the model. The LP model looks like that. It has this part, and this part, those three parts. Okay. I guess that is clear. So we have other examples which are given in the notes. I believe they'll be solved in a similar manner. I don't need to spend so much time on the same case. I think the examples are well illustrated. Should be easy for you to follow. In the example that we did earlier, we had only 2 decision variables. But in the next example here, example 2, where you are told an advertising company is planning a promotional campaign for the client's product, that is sunglasses. The client is willing to spend 5 shillings. That sounds like, sorry about the units of money here. It was decided to limit the campaign media to a weekly magazine. So we have a weekly magazine, we have daily newspaper and TV. So we have like 3 channels through which we can advertise. So the product is targeted at middle-aged men and women, and the following data was collected. So we have the weekly magazine, we have the daily newspaper and the TV advert. And these are the expected viewers, And then we also have the running costs there. So the decision variable in this case is determine the number of advertisements on weekly magazine, daily newspaper, and TV. So how many of each one of these should we run? Okay. How much of each one of that should we run? So as, of course, to maximize profit or to minimize cost. So we are calling those values as X1, X2, and X3. If you want, you can call them X, Y, and Z. But I think X1, X2, and X3 is quite good because it doesn't limit you. Then we want to maximize viewership in this case. We want to maximize viewership. Okay, so then the objective function, this is Z, which will be maximize Z, which where the values are coming from here. Because the weekly magazines, we have maximum viewership of 1.15 and so on and so forth. So that's why we're getting the objective function. Then the resource constraints are obtained from the information which you are given down here, and also the costs. So you can always, sometimes you get questions that require you to do some other calculations, like how to calculate total cost and so on and so forth. But basically, the procedure is the same. Then when you are done with all the basics, you report your model. So that's the model that is required. That's the model that we require. You can do the same with more than 3 variables, like how here we have quite a number of them. We don't need to go through each one of them. But at the end of the day, the model will have the objective function, set of constraints, which are here in this case, and then we have the non-negative constraint. All right, so I want us to move to the graphical solution of such problems. And graphical solution is only limited to problems which have only 2 variables. So the questions or the illustrations that you've seen here with 3 or 4 or 5, the only thing that you can be asked to do there is to formulate the problem, LP, and you leave it there. But solution for more than 2 variables, that is beyond the scope of this class. So what you should be expecting is that you can formulate a problem with n number of decision variables, with 2, with 3, with 4, with 5, with 10. But when you come to solution, you are limited to two variables only.